Hello and welcome to Core Concepts in Robotics. I'm Sanjiban Chaudhary, Assistant Professor at Cornell and Research Scientist at Aurora. Today, we will explore the concept of control. And what better way to begin than by watching Danny McCaskill and his bike hop around from rooftop to rooftop. Whether you find this petrifying or simply beautiful, we can all agree that Danny is in perfect control of his bike. But what is the mathematics of such control? And more importantly, can we ever get our robots to do this in real life? Well, we're certainly getting close. Here are the Atlas robots from Boston Dynamics that are getting better and better at doing backflips. And even more impressive, here is the Starship rocket from SpaceX falling from all the way down from the sky, inverting itself and touching down without exploding. So how is it that we can control these systems to move so precisely where a single misstep could result in an irrecoverable spiral to disaster? The answer lies in the ability to model these systems. We can think of models as simplified abstractions of reality that tell us how inputs to a system affect its outputs. Models are powerful because they allow us to work out the correct sequence of inputs to get the outputs we want, well before we actually try it out. Consider the history of flight. The Wright brothers relied on fundamental aerodynamics models of lift and drag, and a lot of inspiration from nature, to achieve their first powered flight in 1903. Better models and engineering saw the rise of commercial flights that revolutionized transportation. And it is these models that have enabled us to leave our planet and visit other distant objects in the night sky. So yes, models are pretty powerful, but how do we use them for control? A powerful framework for doing this is a Markov decision problem. Let's say we wanted to model a rocket. First, we need to define its state. State is a compact representation of everything you need to know to predict motions of the future. These include the 3D positions and velocities, as well as the 3D rotations and velocities. Next, you have actions. Actions are control inputs we can apply to the rocket to affect its future state. These would be thrusters that provide force in the x, y, and z directions. We then work through Newton-Euler equations, aerodynamics, a sprinkle of parameter estimation, and we have a model for where the rocket will be in the next state. Once we have a model, we can think of control as an optimization over time. The goal is to solve for a sequence of actions, one at each time, that minimize the sum of cost at each time. Cost here captures penalties for not being in a desired state or for doing undesirable actions. Take our rocket at t equal to 0. We're going to try a candidate sequence of actions. The cost can be how far away it is from landing, plus how much fuel we are burning. It's large because the rocket is far from the ground and in the wrong orientation. At t equal to 1, the rocket straightens out, so the cost starts to go down. But at t equal to 2, it overshoots and the cost jumps back up and continues rising. Till at t equal to 3, the rocket crashes and burns. Okay, so that's an example of a not so good sequence of actions. Let's try that again, and this time do a better job. The rocket starts straightening out, and this time does not overshoot, and makes a perfect touchdown. The cost of the final step is 0, since the robot reached its goal and all thrusters are off. So, how do we solve this optimization problem? You might be tempted to do a brute force search over all actions it can take. So, at t equal to 1, you discretize your control space, apply control, and ask your model, what's the next state? Good. Now at t equal to 2, you take every one of those states and branch again on all your controls. You can see where this is going. The search tree becomes bigger and bigger with time, growing exponentially large in size. This is what we call a combinatorial explosion, which says brute force is prohibitively expensive. This may look dire, but fear not. MDPs have a beautiful recursive structure that Richard Bellman discovered way back in 1957. Take a look at the original optimization where we are minimizing the sum of costs at each time step. The optimal value of this term is called the value of the state. Now notice that we can split this optimization and pull out the min over U1. So we get Cx1 U1 plus the optimal value of the next state Vx2. How? Because the model is Markov, the optimal sequence of actions at t equal to 2 depend only on the state x2 and not on x1 or u1. This means we can solve a recursive sequence of nested optimizations to find the optimal sequence. This was Bellman's key insight, which he coined as the phrase dynamic programming. The optimal value of a state is the minimum one-step cost plus the optimal value of the next state. Now, this may sound a lot like good old-fashioned breadth-first search, but we're going to run into a major problem. To fully appreciate it, let's begin by looking at a minimalistic example of balancing an inverted pendulum. While the inverted pendulum may seem like a much too simple problem, it's actually a pretty useful model. Take a humanoid robot. Let's say we wanted to balance on one foot. It too has to figure out a torque that keeps it upright. Or take the example of a rocket that we want to make upright. Again, it has to figure out torque that counters gravity like the pendulum. Okay, let's do some quick math. We will begin by modeling an inverted pendulum. We can draw the pendulum at an angle theta from the vertical line and apply a torque tau. Let the mass of the ball be m and the length of the massless rod be L. We can then write out the Euler equations, moment of inertia times rotational acceleration equal to total torque. With some rearrangement, we get theta dot equal to GL sine theta plus 1 over ml squared tau. Finally, assuming small angles, we get a set of linear second-order differential equations. Now for convenience, we're going to call tau over ml squared our control actions u. Since we're computer scientists, we're going to code this up in a discrete time by integrating the differential equations over delta t. We will define the state as both the position and velocity for Markovianness, and link future state at t plus 1 to current state t and current control action ut. Now a little bit of calculus will give us the coefficient matrix of these two terms, A and B. It's worth noting that the dynamics of this system is indeed linear. Okay, what should we set as the cost? Let's define a quadratic penalty for the pendulum not being at the equilibrium theta equal to 0, theta dot equal to 0. Let's also add a penalty for applying a lot of control input. For example, the squared of control input. So we can call the first term the state cost and the second term the control cost. We often use the term regulator to denote a system that regulates the state, trying to keep it at a set point. Now, just as we did for the dynamics, we can write out this cost in a matrix form. The matrices Q and R denote the cost coefficients for state and action, and thus the cost is a quadratic. Okay, to solve the MDP, let's recall Bellman's insight that the optimal value of a state is the one-step cost plus the value of the next state. Now, as the equation suggests, we are going to iteratively build up this value over time. Let's try to visualize what this computation looks like. This arrow shows the arrow of time. Each vertical line here denotes the state of the robot at time equal to t. I know the state is 2D, but let's squash it to 1D for ease. For example, this point represents a state 0, 0 at time t. Other points represent states further away, for instance at higher angles and higher velocities. For example, the state at the bottom represents a pendulum falling to the left, and the state at the top represents a pendulum falling to the right. And at each time, we can compute different states. Now, what is our goal? We want to compute control actions that progressively drive the system towards the origin without spending too much effort. So, recall Bellman's equations. We can write down the current value at time t as the min over one step cost plus the future value at time t plus 1. Now, the idea is simple. Begin at the last time step and compute the values backwards. Okay, so let's only focus on the last slice of time. For every state at this time, t, we have to compute the value for each state. Okay, so what is the value of the last time step? It's simply the cost at the last time step, half xt q xt plus half ut transpose r ut. And if you take the gradient of this value and set it to 0, it simply says you should set ut equal to 0. This says don't do anything at the last time step because you'll only pay a price. The value then is simply the state cost, which is a very nice quadratic with a coefficient q. We're going to call this coefficient vt, which will come in handy in a minute. Now you can imagine every dot in this line computing values. For example, the origin has value of 0. The point 0.5 has a value of 0.5. Similarly, as the further you get away from the origin, the more your values are. In fact, they increase quadratically as you go away from the origin. So you get a nice quadratic bowl. Now for the interesting bit. Let's look at time step t minus 1. Once again, we have to compute values for all the dots on this slice of time. Recall that at time step t, the value is a quadratic. Once again, Bellman tells us that the value vt minus 1 is min over ut minus 1, the one-step cost plus the value at the next time step. So you can plug in this one-step cost and plug in the value at the next time step and simply compute this value, right? This gives us a computational procedure. At every state, try every action and add up the quadratic cost of that action plus the quadratic value of the next state. Take a min, do these for all the actions, and you get a value. Wow, so if you just grid up the value function at time t and keep repeating this recursion, you should just be done, right? Not so fast. Let's ask a basic question. How much memory do you need to store VTXT? Consider our Atlas robot. Let's say it has 26 dimensions, and let's say for each dimension you spend about a kilobyte of memory. That means you need to spend 10 to the 76 bytes to save the value. That's a lot of memory, orders of magnitude more than the memory we have generated till date. This is famously known as the curse of dimensionality. It's a nightmare that haunts us all as roboticists. But perhaps this curse is merely pointing out a question we're all thinking. Do we really need to numerically compute the value for all states? What if we could analytically compute this value function? The answer is we can. Let's do some back of the napkin math to convince ourselves. Suppose the cost function is 1d, so cxt ut is equal to half qxt squared plus half r ut squared. Let's also write the value function in 1d, so vt plus 1 xt plus 1 is equal to half vt xt plus 1 squared. Plug in a linear dynamics and you get a quadratic value. Now we bring in Bellman. The value vtxt is equal to the one-step cost plus the value at the next state. Note that since both are quadratic, we can just write down this term as a general quadratic. Now here's the cool bit of math. If you take the gradient with respect to ut and set it to 0, you see that ut is actually linearly dependent on the state xt. And if you plug this back in, you get a quadratic. So, the value at t plus 1 is a quadratic implies the value at t is also a quadratic. And so, you start with a quadratic at t, and get a quadratic at t minus 1, and another at t minus 2, and it's quadratics all the way down. The optimal value function is always a quadratic, and this quadratic coefficients can easily be computed analytically. This is the fundamental property of LQR that makes it such an attractive model. Let's derive the same update, but this time let's do it in matrix form. So, the value Vt is equal to min over ut, the one-step cost cxt ut plus the value at the next step Vt plus 1 xt plus 1. Plug in the quadratic expression for the one-step cost, and plug in the general quadratic formulation for the value at t plus 1. Next, we are going to plug in the dynamics xt plus 1 as a linear function of the state xt and the control action ut. Just as we did for the 1D example, we are going to set the gradient to 0. If you do that, you can see that r times u plus b transpose vt plus 1 axt plus b transpose vt plus 1 but is equal to 0. And with a little bit of algebra, you can write u as equal to minus r plus b transpose vt plus 1 b inverse b transpose vt plus 1 axt. And the cool thing is that the value is a linear function of the states. So there's a linear mapping from states to actions. Now plugging this back in to our original value gives us the expression vtxt equal to the half xt transpose qxt plus the rest of the expression where you've plugged in ut equal to ktxt. And if you separate out the xt terms, you get a quadratic on xt. In fact, we get a really elegant expression for updating the value coefficients over time. So the value at time t is linked to the one-step cost matrices, the gain matrices, and the value at the next time step, t plus 1. This suggests a very simple 3-line algorithm for computing a controller for our inverted pendulum. Step 1. Initialize the matrix Vt with Q, the state cost matrix. Then we are going to loop backwards in time. So every time we are going to compute the gain matrix Kt, which is simply a function of the coefficient matrices and the future value matrix. We are then going to update the value matrix and repeat. And this is all there is to the LQR algorithm. This is an animation of the value iteration for the inverted pendulum when we go backwards in time. This is exactly the equations we just wrote down. And you can find a link to the notebook that generated this in the description. The value increases as we go from yellow to red. So the value function at t equal to 100 starts off as a quadratic, but as we go backwards, it starts to skew to the left and eventually converges. We'll talk about why it's skewed in a second, but first note that it's not too surprising that the value is converging. Why not? Because if the system is stabilizable, all points can be driven to the origin, and so their values must be bounded. In fact, we don't even need to do this iterative process. Instead, we can solve what are called Riccati equations to get this fixed point. Now, back to the question about why the converged value function is skewed. It's an interesting question. First, consider the top left and bottom right corners. The value appears to be super low here. Why is that? Well, look at the angle of the pendulum and the angular velocity. They have opposite signs. So, the angular velocity is pushing the pendulum towards the origin, giving us a momentum in the right direction. Okay, now look at the top right and bottom left corners. The values here are really high. This time, the angle and the angular velocity have the same sign. So the pendulum is moving faster away from the center. It's pretty cool that the math just tells us that this intuitive fact about what are easy and hard states. Now let's actually try our controller out. We'll start from the easy position. I added in a bit of noise to make the controller work just a little bit harder. Still, it pretty quickly reaches the origin and stabilizes along that. Notice how it walks along the diagonal. This is because this is the path of least action. Here's another starting point from the flipped position. Again, it walks along the diagonal and makes the pendulum stand upright. Okay, now let's pick a hard starting point, where the pendulum is falling away from the vertical. See how the controller first arrests the fall, then builds up enough angular velocity in the other direction to turn it into an easy problem and get it into the goal. Here's another hard starting point from the flipped position. It's super interesting to see the path it takes on the value function. It doesn't follow a straight line to the goal like the easy case, but rather an arc. Part of the reason is simply to do with the dynamics of the pendulum. It has 2 degrees of freedom, theta and theta dot, but our actions have only one. So we can't trace out arbitrary paths over states. The other reason is that this arc happens to be the path of least cost, as the contours of the value function indicate. Any other action at any point along the arc would only go uphill on the value. And this brings us to the end. To summarize, a powerful way to think about control is as a dynamic optimization, where the goal is to compute a mapping from states to actions that minimizes a user-specific cost. For example, land a rocket without exploding. Moreover, you can do this efficiently thanks to Bellman's insight that the optimal value of a state at your current time is simply the minimum one-step cost plus the optimal value at the next time, suggesting an elegant iterative procedure. But you can't naively apply discrete search, because then you'll be cursed by the demon of dimensionality. The amount of time and memory you spend grows exponentially with how many dimensions your robot is in. Thankfully, there's a beautiful analytic structure that comes to the rescue. If your dynamics are linear and your costs are quadratic, then your value of your state is a quadratic. And we can update the coefficients of this quadratic analytically. And with that, we've reached the end. We probably left with more questions than when we began. For instance, we know that the humanoid is not linear. How can I use this for nonlinear systems? Or, what happens when I don't know my model? In future lectures, we will cover core concepts on these topics. But if you would like to wade into deeper waters, I highly recommend Russ Tedrick's beautiful set of lectures on underactuated robotics. Till next time.